Let's now welcome Professor Nelly come up on stage as our second speaker for this afternoon. So this morning we heard about Professor CM Yang's presence and influence in Singapore research community. And actually we are very pleased to have Professor Nelly this afternoon because she herself is a CM Yang scholar. Okay, so she herself is a reflection of CM Yang's influence in Singapore. Also this morning from Professor Auping's talk, we learned that it was regarded by Einstein that thermodynamics is very solid, very hard to be challenged. But as you can see from Professor Nelly Ng's talk, she's going to introduce new approaches nowadays to do thermodynamics. Let's welcome Professor Nelly Ng.
Okay, thanks Prof Gong for the introduction. It's a great pleasure to be here and to speak. My name is Nelly. I'm an assistant professor here at the SPMS NTU, but I think more importantly, today I am here as an alumni of the CN Yang Scholars Research Program. And it wasn't the first time I've actually encountered Professor CN Yang. I still actually remember being a high school student back in Malaysia, and one day arriving at my school in the morning, and realizing that our physics high school teacher actually took the trouble of applying to bring a bunch of hyperactive 16-year-old kids to the Malayan University. So we could listen to a public lecture given by CN Yang on the topic of symmetry. And that for me was a very beautiful memory, especially for a very young student, enthusiastic about physics, but at the very beginning of my own journey as an academic. So when I enrolled in NTU as a CN Yang undergrad scholar, I had tremendous pleasure in making many new friends, many like-minded friends in the program. So unfortunately, I think I wasn't very good at keeping photos, so I have very few nice ones to share. But during these years, we actually had several opportunities to meet and hear Professor Yang speak, and these have been very inspiring sessions for me. So one of them was in 2010 during the Murray-Gell-Mann conference. So although the CN Yang program, I think, has evolved and improved over the past many years, I think the spirit remains largely the same, which is that we are a group of scholars coming from very diverse academic backgrounds, but we are quite united in our appreciation of the natural sciences and our enthusiasm when it comes to learning and research. And as a result, as an undergrad, I had a fabulous time here. I learned together with my fellow students and learned from them. And this is so much so that even if I look back many years for my own scientific education, most of the friends that I still remain in contact with and still have very good friendships with today are my fellow CN Yang scholars from 10, 15 years ago. So one thing that the CN Yang program has definitely shaped in my academic life is the appreciation of subjects that are multidisciplinary in their nature, where you allow for the insights and tools from very different research communities to come together and form something new. So today I've chosen to talk about the topic of quantifying disorder, in particular using entropic functions, which are used across many disciplines. So we will have a look at that. But very quickly into the talk, you will also realize that a quantification of disorder often also leads to quantifying resources and information. And I will go into that. So let's start. I apologize for many equations in my slides, but that's how it is, no? So the entropy is a function. It is evaluated on a state that describes a system. So in the classical world, the system state is very often described fundamentally as a random variable and characterized by some classical probability distribution. But in the quantum domain, this is in general a density matrix, rho. In other words, this is a linear operator where the eigenvalue spectrum would form a classical probability distribution. And the entropy is then given by this function, which is actually an expectation value of this variable, which is minus log of rho. This is otherwise known as the surpriser. And this is a function that goes to zero the more pure or the more deterministic, predictable your state is, and it becomes larger when the state is unpredictable. This is not the first phase of entropy. I must say that entropy has had many different phases, and its behavior has been one of the mysterious subjects in the 20th century physics, emerging from a very long history of studying the second law of thermodynamics. So here we have the pictures of two scientists. One of them is Boltzmann. He was the first one to write down the thermodynamic entropy, not in terms of macroscopic variables, such as heat, temperature, the things that we are familiar with in classical thermodynamics, but he wrote it down as a function of microstates in the system. So in some sense, that signified kind of the birth of statistical mechanics as we know it. Following this, we had Gibbs, who then refined the study of entropy to define various statistical ensembles in physics. But the physical meaning of entropy eluded us for a while. And as physicists even delve deeply into the regime of non-equilibrium quantum systems, we are forced to abandon many of the concepts that we had and cherished in classical thermodynamics, for example, temperature. We learned that we cannot take it for granted. But entropy is one of those quantities that kind of seen refinement and robustness that helps us continue to still understand thermodynamics for quantum systems. Now, somewhere along the line, we actually see a plot twist, which is that the entropy function actually starts to emerge in a completely unrelated field, seemingly unrelated, which is the theory of communication. So Claudius Shannon was the pioneer in this, and during war times, he was setting out to understand how information can be digitized and transmitted in a reliable way across, let's say, a noisy process channel. And Shannon showed that the maximum achievable rates on digital communication were very strongly tied to the entropic function when you evaluate it on the message and on the process that transmits the message. So the unexpected meeting of these two fields kind of sparked a deeper understanding on entropy and what it actually fundamentally captures. And today, we see entropy used everywhere, especially when it comes to quantifying properties like complexity, entanglement, or just information processing in general. Entropic analysis has even found its use in topics which are much far from science, such as economics, etc. Essentially because it is getting at the very fundamental level of describing how information and disorder propagates under very generic processes. So as one delves deeper into the study of entropy, one of the things that we quickly see is actually a slightly different quantity is much more useful. So instead of studying just the entropy of a state, a more useful quantity is called the relative entropy, which takes in two different states. And it's more useful because it reflects the fact that we are quantifying disorder, mostly taking into account some reference state. So here in the slide, this is denoted as sigma. Now, a simple example of this is actually in the realm of thermodynamics, where a natural reference state is precisely the state where the system has thermalized and starts to have a well-defined temperature, just as its surroundings. So the relative entropy with respect to that thermal state is then exactly what gives us things like non-equilibrium free energies that will tell us how much work we can extract from a quantum out of equilibrium systems. And this results hold even when we see a breakdown of classical thermodynamics. Now, the reason why all of these areas can be studied via the relative entropy actually points to a more fundamental reason, namely that many of these questions in these fields can be cast as special examples of a more generic framework. And this is called the resource theoretic framework. It's actually a very simple but powerful idea. So I'm going to go through it a little bit. So any resource theory would start by identifying two different elements. One element is a set of free channels, denoted by S here. And this would be the channels that you have freedom to use and generate an unlimited amount of them. The second element, being free states, denoted by M, would be the states that you can generate arbitrarily many copies and use them freely. You can think of these two elements as stating some sort of rules of the game, and you can always operate within these two elements. And now the essential question boils down to the following. Suppose you start from some initially prepared state, which is useful, and your goal is to reach a particular target state, rho prime. Then the question is it possible for you to do so, just by using the free states and the free channels? So to see why this can be a very useful language, consider the case of a resource theory used to describe entanglement. You have two parties. So Alice is on the ground, and you have Bob. He is on the space station, and they want to communicate quantumly. The one way to do that is, of course, to establish high-quality entanglement between them. But because of the big distance and noise, what they can manage to share are mostly very noisy versions of entangled states, which are quite useless for communication. But on the other hand, classical communication is fairly advanced and noise-free. And on the other hand, Alice and Bob, we often assume to have powerful local quantum labs, which allow them to store, to manipulate systems locally. So we can assume that Alice and Bob actually have access to what is called LOCC, local operations in classical communications. And now, if one can show that using these operations, you can take a bunch of very noisy entangled states and kind of do a distillation process so that you get a small amount of high-quality entanglement, then that would be very practical. It would be useful. So the resource theory framework seems very generic, and yet it is very powerful because many problems in quantum information and processing can be rephrased as a resource theory. So here are some examples. One of the archetypical examples is to consider the set of maps that would preserve a maximally mixed state. And this is usually critical for the study of quantum randomness. And we've talked about thermodynamics. So casting thermodynamics into a resource theory actually gives us a new fundamental tool in studying thermodynamics out of equilibrium in a quantum regime. And it complements the existing studies of quantum statistical mechanics and open quantum systems. Lastly, we are also starting to see that the resource theoretic framework helps us to distill exact resources that make quantum computing tick. So this is known as the stabilizer resource theory. And there are many more, actually. Non-Gaussianity, non-Markovianity, anything that quantifies a certain valuable resource under limited operations usually can be rephrased into a resource theory. So what can we do with this is the question. And one of the most well-known general results in resource theory is found in the so-called IID limit. So IID stands for identical and independently distributed. It means that one has access to an initial state that is composed of many identical copies that are uncorrelated from one another. So this is denoted as rho tensor n in the slide. And secondly, limit would mean that you are ultimately concerned about the highest rate where you can take these initial states and transform them into r times n copies of your target state, rho prime. And one can see that this assumption of IID actually resembles some of the assumptions we have in thermodynamics. So to allow for this, we have to allow for a vanishing amount of error in this IID limit, it seems like a technicality, but it's actually very critical for our analysis purposes. And a famous result for resource theories in the IID limit is to say that in some cases, when the set of free states and channels satisfy a few kind of generic conditions, then we can determine the asymptotic rate of transformation, the highest rate. And furthermore, this is directly given by the ratio of relative entropy evaluated on the initial and target states. Because this asymptotic rate is given by a ratio, and it holds for all initial and target states, it means that according to this limit, you would have reversibility. You can start from rho tensor n, distill to a small copy, and you can try to reverse the process, and you would get back your initial state and not lose anything. So it goes without mentioning that the IID limit is, of course, an ideal simplification. Because in real life, you don't have infinite number of identical copies. These assumptions are indeed quite strong. So instead of looking at the IID limit, the exact opposite would be to consider what is called a single-shot process, which essentially means what it sounds like. You take a single copy of rho, you think about whether it's possible to deterministically transform it to a single copy of rho prime, or maybe do it probabilistically with some fixed value p. So this is a different, this is a more unassuming kind of scenario. And just from understanding how relative entropies behave on a very generic level, we can deduce that actually the transition is going to be possible only if the ratio, which was what given us the rate, was larger than 1. So if we now move the denominator across the other side, you see that this means the relative entropy has to decrease in the process. So we call such functions a monotone of the resource theory. So one of the things that we see for single-shot processes is that the relative entropy is no longer enough to just single out one condition that guarantees us the possibility of state transitions. And this is because of the existence of different other monotones. And this is, again, one of the most prominent examples that we have is in the resource theory of thermodynamics, where the free states and channels are really very general. They talk about energy conservation, they talk about using free states with a well-defined temperature, and they set out to capture fundamental limits to what we can do. And yet, in the single-shot case, we see actually a huge bunch of additional quantities, and these are called the Renyi relative entropies. And these Renyi relative entropies would jointly determine if a process is achievable or not. So these, the existence of these extra quantities actually make the single-shot limit very hard to analyze, because if you want to apply them to problems, now you actually have to perform an optimization over all these entropies, and there's no telling how they behave for particular states. I should also mention that it gets even more complicated when you talk about general density matrices, because there's no one particular generalization of how to define Renyi relative entropies for the quantum regime. Now, we have seen two different regimes. They are extreme cases. One has a very strong assumption on the structure. One is almost totally unassuming, but it ends up with a condition that is very hard to evaluate. But more often, we are actually in the middle, in an intermediate regime, where we have some finite number of copies of n, and we can safely say that within this finite n number, you have identical states that are uncorrelated. And furthermore, we say we tolerate some small amount of finite error. And the nice thing is that we actually know something about this regime very rigorously. We are able to quantify the approximation of the rates achievable to be very close to the asymptotic rate, but with correction terms that would vanish as n grows large. And the function f here, which is the correction, is characterized very often by something called the relative variance. Okay? We will talk about that a little bit later. But the intermediate zone, and in particular the relative variance, is actually very unstudied, I must say. So we don't have as good as a hold on how this quantity would behave generally in a resource theoretic framework, as compared to all the other entropic functions that we have seen to date. So summarizing a bit, 3 regimes, all kind of different and all involving different quantities. On the IID case, you have just the relative entropy. On the single shot case, you have a whole family of Renyi entropies. And to simplify the analysis, some of them look at just the min-max entropies. And then you have the intermediate regime, where the relative entropy comes in very strongly with the relative variance as a correction term. So the relationship between these regimes should be more or less clear, because we know that the single-shot regime doesn't make particular IID assumptions. So if we evaluate the results in this unassuming picture and take the appropriate limit, we should be able to recover results in the intermediate regime and the IID limit. And this is very well studied. It goes under the names of asymptotic equipartition theorems. But here is where we start to, in the past few years, encounter a little bit of a plot twist, which is that we start to see that some interesting relaxations in the single-shot regime start to allow us to wash out the effects of these additional monotones, the Renyi monotones, and leaving again the relative entropy to be one of the few key quantities characterizing the transition process. And this is, just to say a little bit more about this, it's when the process is still single-shot, but a high-dimensional ancilla or catalyst is allowed to come into the picture. It's allowed to be correlated with the system under the condition that it should change, it should remain unchanged locally after the process. And this was shown to eliminate a lot of Renyi entropies, which would give you strong finite size effects. And I must say that this mysterious effect of correlations with an external catalyst is something that the quantum information theorists are not fully understanding yet. So it remains a little bit of a mystery to us. And so one of the natural questions is that, well, do we ever see the relative variance popping up in the single-shot regime? And when does that happen? It's one of the questions. Of course, it's not only the only question, because on the other hand, we know that in the IID limit and single-shot limit, we have monotones, and they characterize state transition processes. So similarly, one could ask, what about the relative variance? Does it behave monotonically? Because if it does, then that gives us some sort of arrow of time that guides, how the state would travel through the state space along with a set of operations. So very recently, by studying the properties of these relative variances, my colleagues and I made a first step to answering the 2 questions in an affirmative way. So our results can be found in the following paper. And this is really just a first step because we derived these conditions in a limited context. So there are terms and conditions attached to the results. And these terms and conditions are specifying a subclass of resource theories, those which are called majorization-based theories. And secondly, they also are derived for a subset of states instead of the full set of quantum density matrices. Nevertheless, it's a useful first step because it helps us now eliminate, in some cases, the need for studying and optimizing over complicated of Renyi-like quantities whenever we want to apply them to study certain problems. So let me just use a couple of minutes to show an overview of 2 technical results that are fleshed out in the paper. So first of all, under the terms and conditions, namely incoherent states and majorization-based resource theories, what we managed to show is that if I want to determine if a state transition is possible, namely rho going to rho prime under that resource theory, I can, instead of checking the whole spectrum of Renyi quantities, I can check one. And this inequality involves the relative entropy, and it involves the relative variance. And when this inequality is satisfied, I actually know that the transition would become possible. And the reason why this happens is because we show a more technical lemma that spells out why this happens. And this is because the relative variance actually gives a direct bound on how the smooth Renyi quantities would deviate from the relative entropy. So it would contain most of the information that we need to put bounds on all the Renyi relative entropies. So we were able to then take our new result and study a few kind of problems that were lying around the field of quantum thermodynamics. And what we quickly noticed was a couple of well-known established results, which actually required very extensive and complicated proof techniques. We could actually recover them by using, at least recover the qualitative essences of those results with simple algebra techniques added onto our new understanding of the relative variance. So that seemed pretty cool to us. A second result is regarding the monotonic property of the relative variance. So very quickly, we were able to ascertain that the relative variance is not something that by itself gives us an error of time. It's not a monotone. You can find very easy examples that would violate that. However, what we see is when jointly considered with the relative entropy, we can make some interesting new monotones that would help us determine state transition. So the lemma here is spelling out exactly one of these new monotones that is a function of both rel entropy and rel variance that would give us additional conditions on the monotone. So I guess one can always write down certain monotones, and the question is, why are they interesting? Do they actually help us in understanding processes in resource theories? So one key difference about this monotone that we have is that compared to all the other Renyi quantities, they have the restriction of being additive under tensor products of systems. So if you evaluate the Renyi quantities on tensor products, then they turn out to be additive. It means that the entropy will just be each local quantities added all together. But our new monotone is actually non-additive because of this combination of entropy and variance. And this property of non-additiveness actually help us to use it as a new tool, as a new edge, to probe problems that were not before possible with the Renyi quantities. So one problem is in thermodynamics as well. It's the problem of entropy production. And this is a well-known result in quantum thermodynamics that if you talk about processes, that entropy always increases. And what we have with this resource monotone is tighter positive lower bounds on the change in the entropies in the system. So a second situation is actually when we study, again, the problem of catalysis, because this is remaining to be something that is very less well-known in the community, where we can make use of this new monotone to give bounds on how large does a catalyst need to be if it were to catalyze a transition. And this is actually, I must say that to my knowledge, no such results, or very, very few such results exist on giving requirements on what the catalyst needs to be in order to catalyze a particular process. Our work, when applied to this scenario, actually helps us to give a lower bound on how large the catalyst needs to be in terms of its dimension to catalyze a particular process. So I think I still have some time, yes?
Yeah, no time left.
Oh, sorry. It's good. So these results are kind of built on really painstakingly proving certain mathematical properties of the RELVAR. I had a lot of pain and a lot of fun doing them. So this is a very small conclusion of what I have been interested in. And indeed, it is kind of a mathematical and technical subject to concern myself with properties of functions, whereas the applications might not always be very immediately obvious, but there seems to be intermediate steps that we can take towards applications. Nevertheless, as a theorist, I will never let that deter myself from having fun studying structures. I think, as usual, there are actually many open problems to continue to solve in this field of general resource theories and looking at how to quantify rates of transitions. But I somehow, I hope I have somehow managed to entertain you for the past 30 minutes or so. So if you have questions, I will be glad to answer them. And thanks for listening.
Yeah, thank you very much, Professor Ng. It's actually 30 minutes already. Nevertheless, apparently you have intrigued our audience. I have many questions here. So I will probably take the first question, okay, as I can see. The question is very big and a very serious question, okay? So let me read it aloud. Taking into account your research, how would quantum communication be used to resolve conflicts that we encounter on a daily basis? Would it work on a large scale, such as a Russian invasion of Ukraine?
Can I actually read it? May I?
Yes, you can.
Come and read it? So I understand the question. Okay. Quantum communication we use to resolve conflicts.
Our daily conflicts. Mm-hmm. Thank you.
So the question is, how would quantum communication be used to resolve daily conflicts in society? This is such a big question, a very serious one. So quantum communication, just like classical communication, has the aim of providing security or secrecy when people communicate through channels. And I think they exist. I think technology is always improving with the same goals in mind and finding better and better ways to do that. And I think digital communication, computation are powerful tools that allow us to do these things, and which is why everyone works on them so much. But I think the applications are immediate, but yet also in the long run. I think we have a lot of work to do to actually, bring these systems into maturity, commercialization, and so on and so forth. I think I study them for the fun of it, I must say. But I also think that it's important. For the physicists, we are always concerned with the details, the science behind things, and I think it's important to use that for good purposes. But it's also equally important to make sure that people are educated to be kind, be good, and to have moral standards, because ultimately a lot of what people can do in terms of technology and restriction would be a safe net. But to fundamentally change society and bring more good into it, people's hearts need to be changed. I'm not sure if that is a problem that science will, do the most effectively. I would say that science and morality or humanity need to progress in parallel. Otherwise, we will be giving humanity weapons, in some sense, no? Sorry if it's a bad answer. That's more or less on top of my head.
Okay, thank you very much, Professor M. Thank you. Due to time consideration, we have to move on. And also would like to thank the audience for raising so many good questions on quantum communication. Sorry we don't have time to answer each of them, But nevertheless, I think it's the responsibility of educators in Singapore to reach out to the students, to the public, to let people really know what quantum communication can really do for Singapore. Thank you.